Alright, silly people, here's the situation. We're going to be normalizing a wave function. It just so happens that this wave function is for the finite square well, with the even class of solution, given by this piecewise function here. And, just to be completely transparent, I'm going to extend this to make it a little bit more verbose and say that this is the same here, x greater than a. This is d cosine Lx for 0 less than x less than L. Or not, that shouldn't be L, that should be A. Got him. And then this is going to be d cosine of minus Lx for minus A less than x less than 0. And then this is going to be f e to the kappa x, positive kappa x, for x less than minus a. Right. And so this is going to be a big square modulus then. So we're going to have an f squared integral from a to infinity e to the minus 2 kappa x dx. And then there's going to be a d squared from 0 to a cosine squared Lx dx. There's going to be a d squared, actually minus a to 0, cosine squared minus Lx dx. And then there's also going to be this f squared term at the end, which goes from minus infinity to minus a of e to the 2 kappa x dx. I'm going to make a couple different substitutions first, creating this new variable, which I'm going to call u, which is going to be 2 kappa x minus 2 kappa a. And then the differential of which is just 2 kappa dx. And so that's going to be what we're going to use to deal with the first f squared integral. The next f squared integral will be dealt with by a variable u, which I'm going to define as minus 2 kappa x minus 2 kappa a. And then the differential of that is just minus 2 kappa dx. And that's going to allow us to write those f squared integrals in a certain way. Namely, we've got f squared over 2 kappa for the first one, right? And that's going to be the integral from a to infinity. Notice if you plug a for x into the definition of u, you get 0. So actually this is 0, and infinity is still infinity. And we have e to the minus u du. But also with an e to the minus 2 kappa a here. That's going to be tagging along. The other f squared integral is actually minus because the differential was minus. So we get 2 kappa here. But then this is minus infinity. If you plug it into here, you get positive infinity. And then in here, if you plug in a, you get 0. Or minus a, you get 0. Yeah. And then this is e to the minus v dv, and we still have this weird exponential left over. And then the d squared integrals, I'm just going to do from a table integral. This is 1/2 x plus 1 over 2l sine Lx cosine Lx. And that's from 0 to a, and then there's the other d squared integral, which is still 1/2 x, but then minus 1 over 2l sine minus Lx cosine minus Lx. And that's from minus a to 0. Cool stuff. Both of these integrals are ones which we know how to do. They actually have the same value, because if you just flip this minus sign to a plus sign and flip these integration bounds, it's the same integral, which has the value of 1. So we can add those up. That's going to be f squared over kappa e to the minus 2 kappa a. And then plugging in the bounds for the d squared stuff, we have d squared, and then this is going to be a over 2 plus 1 over 2l, 1 over 2l sine LA cosine LA, and then if you plug in 0 for x or for sine of x, you get 0, so we'll close it off there. We also have another d squared term. The minus, if you plug in 0, you get 0 again, but if you plug in minus a and then flip the sign because it's being subtracted when you evaluate it, you get a over 2 plus 1 over 2l sine LA cosine LA. So it's the same term as that one. So that's kind of fun. We can simplify this as well, and we're going to have to, by using a definition. Well, it's not a definition, it's a consequence of a boundary condition that Griffiths defined, where he got a form for f e to the minus kappa a equals d cosine LA. And if you actually square both sides, you see we have this term and this term match. And we can plug that in there. So that's what we're going to do. We're going to say that this is now d squared cosine squared LA all over kappa plus d squared, and this is adding these up, it's going to be just a plus 1 over L sine LA cosine LA. And then we can set that equal to 1, because that's what we've been doing this whole time. We've been normalizing it. And so we can get a form for D from this. It's a big, ugly term, because it's just going to be 1 over the square root of cosine squared LA over kappa plus a plus 1 over L sine LA cosine LA. But one of the other consequences from boundary conditions which Griffiths got, he said that kappa equals L tangent LA, right? So we can actually change kappa out for that. And that's just going to make this into square root cosine squared LA over L tan LA plus a plus 1 over L sine LA cosine LA. And to simplify this, I'm going to multiply everything in the fraction by just L tangent LA. So we got L tan LA up here, but now this is, hello, garbage. We got cosine squared LA down here plus AL tangent LA. And then the L will cancel out the L, and then sine cosine over sine. it's sine squared, right? Because the cosines will cancel out and you end up with an additional factor of sine from the tangent. But yeah, and that's cool because we know that sine squared plus cosine squared is 1, so we'll just write it like that, 10LA over 1 plus AL 10LA. And then it's even prettier when you plug in this definition again and just say that this is kappa over 1 plus kappa A. Okay. And then, so that's D. We can also figure out F just from this relation up here. So it's going to be e to the kappa A cosine LA, and then times this funky little radical. But yeah, get normalized.